Hello my dear students, welcome to IMS GATE Academy GATE Foundation course on digital circuit subject. This subject is common for 4 branches: EC, Electrical, Instrumentation, Computer Science. So in this particular session, we are going to discuss the next topic, that is binary codes. So this is the last topic regarding first chapter. So in the previous session we have discussed regarding unsigned numbers and then signed numbers. Unsigned means we no need to represent any sign in front of the number, right? Whereas signed numbers means we are having set of both positive numbers and negative numbers. That time it is mandatory to represent the sign in front of the number. Okay. So regarding signed numbers in binary, how to represent? Regarding that, we are having 3 forms: sign magnitude form, 1's complement form, and 2's complement form. So in the last session, we have discussed regarding these 3 forms in detail, how to represent any sign number, that means any positive number or any negative number, how to represent in sign magnitude form, 1's complement form, and 2's complement form. And we have discussed variety of questions regarding these concepts as well. Okay. So if any of you couldn't attend the last session, kindly watch that session in your free time. We have discussed variety of questions regarding these concepts, and we discussed both conventional approach and shortcut approach as well. Okay, right. So in the last class, I couldn't get time in order to discuss among these 3 forms, which form is the best method or best convenient form in order to represent for the signed numbers. Okay. Now I will give the conclusion point. So can you guess among all these 3 forms, which form in general will prefer? Among all the 3, which is the best form or in general will prefer? Any guess? Yeah. So just by observing here, the first one is sign magnitude form, next one is 1's complement form, and the last one is 2's complement form. Since we are having 3 forms, among all, since this is the last, obviously you can guess that 2's complement form we will prefer when compared to other 2. Okay. Now let us see why we will use 2's complement when compared to other 2. Okay, right. Say for example, for the time being I am considering 4-bit. For the time being, let us assume a number 4-bit. Okay, right. I want to represent plus 0. I want to represent plus 0 in sign magnitude form, 1's complement form, and 2's complement form. Right. So according to sign magnitude form, if you are having positive sign, that means sign bit should be 0. Sign bit should be 0. And regarding the magnitude, you are having 0. That means simply the other bit should be 0. That's all. Because you are having magnitude is 0. Since total number of bits are 4, among that we have considered 1 bit as 0. That means remaining 3 bits are simply you can put zeros. So this is the method we will follow for sign magnitude. Sign magnitude form means whatever the sign you are having, regarding that 1 bit we are reserving. Okay. So since you are having positive sign, sign bit should be 0. Regarding the magnitude of the number, remaining bits. For the timing I have considered for 4-bit. Okay, right. Whatever the representation you are getting, 4 zeros for plus 0, the same representation is applicable in 1's complement form and 2's complement form. Regarding this, we already covered in the last class. So simply you can represent 4 zeros. Okay, representation of positive number is same in all the 3 forms. Okay, now let us represent minus 0. So according to sign magnitude form, what you are going to get? So here you are having minus sign. That means sign bit should be 1. Sign bit should be 1. And the magnitude 0. That means remaining 3 bits you can put simply 0. Okay, right. So here you are having plus 0, which is nothing but 4 zeros. 4 zeros. Okay. Now if you apply 1's complement to this number, what you will get? You will get minus 0. You will get minus 0. So here all the bits you are having 0. If you apply 1's complement, you will get all the bits are 1. All the bits are 1. Okay, so up to now if you observe, Up to now, if you observe, for plus 0 in sign magnitude form, you are having 4 zeros, whereas in sign magnitude form regarding minus 0, you are getting 1 triple 0. Okay. Similarly, in ones column form, for plus 0, you are having 4 zeros, whereas for minus 0, you are getting 4 ones. In general, in our day-to-day life, we will consider plus 0 and minus 0 as what? Same number 0 only, right? But here you are getting two different representations. You are getting two different representations in sign magnitude form and ones column form for 0. For 0, you are getting two different representations. Okay. Now, if you observe regarding this particular number, if you apply 2's complement for this number by using two-step procedure, if you apply 2's complement, what is the number you are going to get? See, you will start from right hand side, go towards left hand side till you are getting first time 1. You can copy all the bits as it is. So since you are not having any 1, so all the bits simply you can copy. That means if you are applying 2's complement to plus 0, you will get minus 0, right? But by using two-step procedure, in order to find the 2's complement, you are getting the same number. That means in the 2's complement form, we are having unique representation. Whether plus 0 or minus 0, we will represent as all the bits are 0. Simple. Okay. Whereas in sign magnitude form or ones complement form, we are having two different representations. So this is one of the reason. Why we will recommend 2's complement form when compared to other two. I hope all of you got the clarity. The first reason why we will recommend 2's complement when compared to other two. Okay. So just write the conclusion point. In sign magnitude form, and in ones complement form, in sign magnitude form and in ones complement form, we have two different representations. For plus 0 and minus 0. For plus 0 and minus 0, we are having two different representations. Whereas in 2's complement form, we have unique representation. Whereas in 2's complement form, we have unique representation. We have unique representation for 0. Whether it is plus 0 or minus 0, in general we will consider as 0 only. But in the sign magnitude form or ones complement form, we are considering plus 0 as one number, minus 0 as another number. Whereas in 2's complement form, we are having same representation, whether you are considering plus 0 or minus 0. Okay. This is one of the reason why we will recommend 2's complement when compared to other two. Okay. Now I will discuss one more reason why we are recommending 2's complement form when compared to other two. Okay. See, in general, if you want to perform subtraction of two numbers, okay, say for example a minus b, I want to subtract b from a. Okay, suppose, so if you are using sign magnitude form, with the help of this method, if you want to perform subtraction of two numbers, okay, what is the first step you will do? You will cross check among these two numbers which number is greater. Say for example, if a is greater than or equal to b, you can perform direct subtraction. Suppose if b is greater than a, that time you cannot perform direct subtraction. That time you have to take minus as common so that you will get b minus a, right? Then you can perform the subtraction. For the resultant value you are getting negative. So that means if you are using sign magnitude form, whenever you are supposed to find the subtraction, you have to compare those two numbers. Among those two numbers, which number is greater? Okay. So after comparing only, you can perform the subtraction. Whereas if you are using 2's complement method, okay, how easily we can perform the subtraction with the help of 2's complement? Now let us see. So I want to perform a minus b. This one we can write it as a plus of minus b. Can I write like this or not? I have copied a as it is. Here I am having minus b. That one I have written as plus of minus b. Both are same. Now a plus minus b, how you will get? If you are having b as one number, for that number just apply 2's complement. If you apply 2's complement to b, then you will get minus b. Suppose if b is a positive number, if you apply 2's complement, you will get negative number. Or if b is negative number, if you apply 2's complement, you will get positive number, vice versa. Okay, right. So now if you observe, a is one number, and you are having b is one number. Okay, for that number, if you calculated 2's complement, so that means this entire number you can assume like y. Okay, right. Say for example, you are having adder. Adder is a one circuit which performs addition of two numbers a and b. Okay, so the same adder circuit, okay, with the help of same adder circuit, you can get the subtraction output if according to your requirement. See, it is very simple. A number we are giving as it is. Now in this case, the second number is what? 2's complement of b. This entire number you can assume like y. So that means you are having adder circuit. It will perform addition of two numbers a and y. For the timing I am assuming this is like y. Okay, so that means with the help of same adder circuit, you can perform the addition operation, or you can get the resultant output as subtraction based on the requirement. Okay, suppose if you want to get the addition output, that time you will give the inputs as a and b. So that the adder output you will get, the resultant output is nothing but the addition of those two numbers. Okay, similarly the same adder circuit you can use, but now in this case the inputs are a and y. A input I am keeping as it is. Now instead of b, I am giving 2's complement of b, that is nothing but y. So that means with the help of adder circuit, you can get the resultant output as subtraction. That is the beauty of 2's complement. Here you no need to check whether a is greater than or equal to b or a is less than b. Without checking that comparison operation, you can easily perform the subtraction operation with the help of 2's complement method. Here output you are getting subtraction output, final output you are getting subtraction output, but internally you are performing like addition operation. That is the beauty of 2's complement. Okay, so because of these two reasons, we will generally recommend 2's complement form when compared to other two forms. I hope it is clear for everyone. Okay, right. So now in this particular session, now let us start the last topic of the first chapter, that is binary codes. So here you are having two terms. The first term is binary, the second term is code. What do you mean by code? In general, code is nothing but it is having some pattern of symbols, but here we are using the term binary. That means those symbols will be in the combination of what? Zeros and ones. Okay, so here we will use pattern of zeros and ones. Okay, I hope you got the clarity what is binary code. Okay, now let us see the classification of binary codes. So we can classify the binary codes mainly into two types. The first one is alphanumeric codes, and the second one is numeric codes. See, here we are using combination of zeros and ones. Okay, then that particular pattern we are calling it as what? Binary code. that binary codes, whatever the combination of zeros and ones you are having, okay, those binary codes, based upon the application for what purpose we are going to use, based on that we can broadly classify the binary codes into two types. The first one is alphanumeric and the second one is numeric codes. Okay, so all of you write the definition regarding alphanumeric code. Alphanumeric code. See, just observe this particular wording. From here you can guess. You can guess. You are using one binary code. You are using one binary code. That code, with the help of that code, you are representing what? You are representing both alphabets and numbers. Here alpha stands for alphabets and numeric means numbers. Okay. So write down the definition. A binary code is said to be alphanumeric code if it can be used for representing both alphabets and numbers. Now, with this understanding, all of you please tell me whether hexadecimal number system will come under the example of this code. All of you please think and reply whether hexadecimal number system is an example for alphanumeric code or not. Yes, most of you in general will say that hexadecimal number system is an example for alphanumeric code. Okay, so if you are saying that this particular hexadecimal number system is an example for alphanumeric code, then I will ask one simple question. What is the hexadecimal code you are having for the letter Z? What is the hexadecimal code you are having for the letter Z? You don't have, right? See, just read the statement. What we are telling here, you are having binary code. That means it is in the combination of zeros and ones. Okay, that particular binary code, okay, we are calling it as what? Alphanumeric. When if it can be used for representing both alphabets and numbers. You are having combination of zeros and ones. Okay, that particular code we are using for representing the alphabets and numbers. So you are having alphabets like A to Z, okay, and numbers you are having 0 to 9. For representing those alphabets and numbers, we are using binary code. Okay, but here in the hexadecimal number system, what is happening? Say for example, if you are having 4 bits, okay, if you are having 4 bits, there you will get 16 combination of zeros and ones, right? Okay, so up to 0 to 9, whatever the decimal equivalent you are going to get. Okay, so there you will get 0 to 9, and then 10 to 15 you will get. Okay, 0 to 9 you can represent with the help of single digit. There is no issue. But 10 to 15 you cannot represent with the help of what? Single digit. That time we are using what? Alphabets. 10 is nothing but A, 11 is nothing but B, like that. Okay, so here what happened, since we cannot represent 10 to 15 with the help of single digit, that time we are using the help of alphabets. But here what we are telling, we are using the code for representing the alphabets, right? So that means hexadecimal number system won't come under the example of this particular code. Okay, now can you guess what is the code will come under as an example for alphanumeric? I hope all of you are very much familiar. Yes, very good, very good. ASCII code. ASCII code is an example of alphanumeric code. See, whenever you are pressing any key from the keyboard, okay, internally there will be 7-bit code. It is in the combination of zeros and ones, right? So on the keyboard you are having alphabets, capital letters, small letters, and numbers are there. And of course nowadays you are having special characters, etc. Okay, so many keys are there, right? So whenever you are pressing any key from the keyboard, okay, the internal code is nothing but it is in the combination of zeros and ones. Okay, so that code is nothing but ASCII code. With the help of ASCII code, you can represent alphabets and numbers. Okay, I hope all of you got the clarity. Right. Now the next code is numeric code. As the name implies, we are using a binary code for representing what? Only numbers. Only numbers. A binary code is said to be a numeric code. A binary code is said to be a numeric code if it is used for representing only numbers. A binary code is said to be numeric code if it is used for representing only numbers. That's why according to the title, if you observe, numeric code. Numeric means what? Numbers, right? So now we can classify the numeric codes into two types. Numeric codes we can classify into two types. The first one is weighted code. Numeric codes we can classify into two types. The first one is weighted code and the next one is non-weighted code or unweighted code. Non-weighted code or unweighted code. So you can guess here, you are having a numeric code. Okay, that numeric code we can call it as weighted code. Here you are having the term weighted. That means what? You are having positional weights. Okay. So a numeric code is said to be a weighted code if it is having positional weights. If it is having positional weights. So for every digit, okay, according to the position, you will be having corresponding positional weight. If it is like that, then we can call that numeric code as weighted code. Suppose if it is not having any positional weights, then we will call that particular numeric code as non-weighted code or unweighted code. See here you can observe non-weighted, that means there is no weight, or unweighted, there is no positional weight at all. Okay. If there is no positional weight, then that numeric code we will call it as non-weighted code or unweighted code. So can you give any example for weighted code and any example for non-weighted code? All of you quickly respond. Any examples for weighted code and non-weighted code? Yes, BCD code. BCD code is an example for weighted code. BCD code is an example for weighted code, whereas regarding non-weighted code or unweighted code, examples are XS3 code, and Gray code. XS3 code and Gray code. Here we don't have any positional weights. That's why these two are the examples of non-weighted code. Whereas here you will be having positional weights. That's why BCD code is an example for weighted code. Now let us focus regarding BCD code, XS3 code and gray code. We'll discuss these three codes. Okay, how to represent these codes. Okay, we'll discuss in detail, and the application of each and every code we'll discuss. Okay, right. So all of you put the heading BCD code. BCD code. Here you're having BCD. First write the full form of BCD. BCD means binary coded decimal. Binary coded decimal. So what it means, let us see. Here we are using code for representing decimal digits. For representing decimal digits. See, when you are having single digit, when you are having single decimal digit, what are the possible values you will get? If you are having single decimal digit, what are the possible values you will get? You will get 0 to 9. Yes or no? You will get 0 to 9. Zero to 9, 10 possible values are there. Whenever you are having single decimal digit, you can represent any of these 10 possible values, right? Okay. So for representing these decimal digits, we are using one binary code. We are using binary code. That's why the name of this particular code is BCD, binary coded decimal. Okay, right. I hope all of you are very much familiar regarding binary, how to represent the decimal numbers in binary. Okay, so when you're having 4 bits, the corresponding positional weights you will get 2 power 0, 2 power 1, 2 square, 2 power 3. So here 2 power 3 is nothing but 8, 2 square is nothing but 4, 2 power 1 is nothing but 2, 2 power 0 is nothing but 1. Okay, so you can call the other name of BCD code as 8421 code. BCD code or 8421 code, both are same. Okay, right. So 0 is nothing but 4 zeros, 1 is nothing but 0001. I hope all of you are familiar for representing the decimal digits in the corresponding binary. 2 is nothing but 0010 and 3 is nothing but 0011. If you are not comfortable, it is very simple, very simple. Here 3 you are having, right? By adding which positional weights you will get 3, 2 and 1, 2 and 1. So for those digits or bit values, you have to consider 1. That's all. For the corresponding bits, you have to consider 1. Similarly, 4 is nothing but here you are having, that means this bit value will be 1, other bits are zeros. Similarly, 5 is nothing but 4 plus 1. 4 plus 1 is nothing but 5. So 0, 1, 0, 1, like that. By adding which positional weights, you are getting the resultant sum. You have to consider the corresponding bits as ones. That's all. 6 is nothing but 0, 110. And 7 is nothing but 0, 111. 8 is nothing but 1, 000. And 9 is nothing but 1001. 100. Okay, since we are having 10 decimal digits, that means for a particular decimal digit, 10 possible values are there. So you will get the corresponding combination in the BCD. That's all. Okay, right. So that means here if you observe, when you are having single decimal digit, the maximum value that you can represent is what? 9. Maximum value that you can represent is 9. So for representing 9, we require what? 4 bits. For representing 9, we require 4 bits. 1001. Okay. So that means, say, for a decimal digit, the maximum value is 9. For represent 9, you require 4 bits in the BCD code. 4 bits in the BCD code. That means, with the help of 4 bits, whether we can represent any of these numbers or not. Yes, obviously, because for a particular decimal digit, since the maximum value, if you are able to represent with the help of 4 bits, obviously with the help of 4 bits, we can represent any of the lower decimal value, That's why it is mandatory that for representing each and every decimal digit in the BCD code, we have to use 4 bits. It is mandatory. So just make a note. We have to represent each decimal digit. We have to represent each decimal digit with 4 bits. We have to represent each decimal digit with 4 bits in the BCD code. We have to represent each and every decimal digit with 4 bits in the BCD code. Okay. Now, in general, if you are having 4 bits, total how many combinations of zeros and ones you will get? If you are having 4 bits, how many combinations of zeros and ones you will get? You will get 16. Yes or no? You will get 16. But here we are using only 10 combinations. Why? Because we are having 10 possible values for a single decimal digit. That's why we are using 10 BCD codes. Okay. But if you are having 4 bits, totally you will get 16 combinations, right? So up to here we got 10 combinations. After this, you will be having 6 more combinations. Okay, 10 plus 6 is nothing but 16. So here you will get 1010, 1011, 1100, 1101, 1110, and 4 ones. Yeah, if you are having 4 bits, total you will get 16 combinations, but out of which we are using 10 possible combinations for the BCD. Okay, what about these 6 combinations? These 6 combinations are non-valid BCD. These 6 combinations are non-valid BCD. Okay, see, it is very simple. For a single digit, whatever the decimal value here you are having, you have to represent the corresponding binary code. That's all. Since for a particular digit, decimal digit, since 10 possible values are there, obviously the corresponding binary combinations are the valid BCD. The remaining 6 combinations are non-valid BCD. Okay, right. So suppose if you want to represent 20 is the decimal number. Okay, 20 is the decimal number. If you want to represent 20 in the BCD code, what you have to do? You have to represent each and every decimal digit with 4 bits. Here you can observe 2 is nothing but 0010, 2 is nothing but 0010, and 0 is nothing but 4 zeros. 0 is nothing but 4 zeros. Okay. So after representing each and every decimal digit with 4 bits like this, here leftmost side you are having 2 zeros. Now in this case, you should not ignore these 2 zeros because of insignificant. Okay. This is the concept we have discussed. When you are converting hexadecimal to binary, each and every hexadecimal digit we will represent with 4 bits. After that, leftmost side if you are having zeros, you can ignore in the integer part. Okay, but here in the BCD code, we should not ignore any single bit. It is must and should each and every decimal digit we have to represent with 4 bits. Now this is the BCD code. Corresponding for the decimal number 20. Okay, suppose if you are having 5 decimal digits, then here how many how many bits you will get in the corresponding BCD? Yes. See, since for each and every decimal digit we have to represent with 4 bits, obviously if you are having 5 decimal digits, you require 20 bits, like that. Okay, right. So you can make a note for generalized case. If there are k decimal digits, if there are k decimal digits, then the corresponding BCD code, will have how many bits it will have? See, if you are having k decimal digits, for each digit we require 4 bits. That means 4 into k is nothing but 4k. It requires, the corresponding BCD code will have 4k bits. 4k bits. It is very simple. Okay, right. Similarly, if you observe here, in general, if you are having 1010, in general, if you are considering 1010, say for example, if it is in the unsigned case, suppose you are having 1010, if you are considering 1010 is in the unsigned case, unsigned, that means all the bits together give what? Magnitude of the number. So 1010 is nothing but 10. 1010 is nothing but 10. Okay. So for the decimal number 10, in order to represent in binary, in the unsigned case, only 4 bits are sufficient. In the unsigned case, only 4 bits are sufficient. In the unsigned case, only 4 bits are sufficient. Now tell me, for representing the decimal number 10 in the BCD code, how many bits we require? For representing the decimal number 10 in the BCD code, how many bits we require? Yes, we require 8 bits. Because we are having 2 decimal digits, we require 8 bits. See, just like this procedure. Here you are having 20. For 2, I have written the corresponding BCD. Similarly for 0. Okay, right. Similarly, here also you can write 10 is the decimal number. I want to represent in BCD. So here 1 is nothing but 0001 and 0 is nothing but 4 zeros. This is the BCD code. Now if you observe here, 10 is a 2-digit decimal number. Okay. When we are able to represent this number with the help of unsigned category or ordinary binary number, okay, since we are able to represent with the help of 4 bits, why unnecessarily we require 8 bits? See, with respect to this is the drawback. In the BCD code, we are getting more number of bits. Okay. Now, you might be, have you ever thought why we are going for BCD? Here actually with the help of less number of bits, when we are able to represent one number, why we require more number of bits? Why we require more number of bits? That is a drawback. That is a drawback in BCD. But now my question is, why we are using BCD code? Where we are going to use the BCD code? Any idea? See, after performing any operation with the help of computer or microprocessor, microcontroller, whatever it may be, okay, after you are getting the final result, whatever the numbers you are getting, resultant number, okay, if that number, if you want to display whatever the final answer you are going to get, with whatever the final result you are going to get, if you want to display that result either in the 7 segment LED or LCD, okay, so in the obviously you can read the decimal number only, okay, you can understand easily, right? Whatever the final value you are going to get, if that frequency is more, that means after performing any kind of operation, whatever the result you are going to get, if you want to display that result in the decimal form, if this frequency is more, that time we will use BCD code, because with the help of BCD code, just by looking at 4 bits, directly you can write the corresponding decimal number. Yes or no? See, if you are having 4 zeros, that is nothing but 0. 0001 is nothing but 1. Even if you observe here, 1001 is nothing but 9. 1000 is nothing but 8. 0111 is nothing but 7. Like that. Okay. Since all of you are very much familiar for 4-bit case. Okay. For 4-bit case, you are very much familiar. Yes or no? Especially for 0 to 9. Just by looking at the 4-bit number, directly you can write the corresponding decimal equivalent. So that's why after performing any operation, whatever the final value you are getting, if that value, if you are supposed to display on the 7 segment LED or LCD, if this frequency is more, then that time if you are using the BCD code, just by looking at 4 bits, directly you can write the corresponding decimal. Okay, that is the beauty of the BCD number system. Whereas if you are using unsigned case, that time if you are doing grouping of 4 bits, which number system digits you will get first? Any guess? We already covered this concept in one of the earlier class. Whenever you are doing grouping of 4 bits in the unsigned case or ordinary binary number, that time you will get hexadecimal digits. That hexadecimal digits you have to convert. Okay, hexadecimal number you have to convert into decimal. That is a 2-step procedure is there. Whereas with the help of BCD, directly if you are doing grouping of 4 bits, directly you can write the corresponding decimal digits. I hope all of you got the clarity why we are using BCD code. Whenever you want to display the results into the decimal form, if this frequency is more, better you can use the BCD code. Okay, you will get more clarity after solving this question also. This is the question asked in GATE EC 2005 for 1 mark. All of you try this question. Yeah, time up. See here, you are having the decimal number 43. You have to represent this number in hexadecimal and BCD. You have to represent the decimal number 43 in both hexadecimal and BCD. So here if you observe, this question is based on 2 concepts. One concept is what? Regarding number system conversion, decimal number to hexadecimal. This we already covered in one of the earlier class, right? And in this particular session we are focusing on what? BCD, right? Binary codes we are focusing. In that, the first code that we have discussed is BCD. Okay, so this question is based on 2 concepts. Okay, so if any of you couldn't attended the earlier classes regarding number system conversions, kindly watch those sessions. We have discussed all the conversions. Okay, in detail we have discussed, and we have discussed the variety of gate questions as well in both conventional and shortcut. Okay, right. So first consider decimal number 43. Consider decimal number 43. Now we want to represent this number in hexadecimal. So what is the first step? Here I want to get hexadecimal digits, right? So what you can do, you can perform repetitive division with the corresponding base, that is 16, right? Sixteen twos are 32. Remainder you will get 11. 11 is nothing but B. 16 zeros are 0. Remainder is 2. So whatever the remainders here you got, you have to consider in the reverse order while you are placing the digits from left to right. Okay. So whatever the digit you got last, that is your first digit, and whatever the digit you got first, that is your last digit. So that means 2b base 16 is nothing but 43 base 10. Yeah, Giritharan, you are getting option C. Okay. We'll check. You can cross check once. Part of the answer is correct. Giritharan, your part of the answer is correct. Up to now we got 2b, right? So regarding 2b, you are having in two choices. That means option A, option D you can eliminate. Sometimes students will do silly mistake here. You are getting B2, right? B2 they will consider, but that is wrong. That is wrong. Okay. You have to consider the last remainder first, and then you have to consider in the reverse order. Okay. You can copy digit by digit from left to right like this. Okay. Right. So regarding the decimal number 43, the corresponding hexadecimal, you are getting 2b. Okay. So this is one approach. That means the decimal number you can convert into hexadecimal by performing repeated division. Okay. Or otherwise, what you can do here, among all the options, the first option is, the first number is corresponding to what? Hexadecimal. The first number is corresponding to hexadecimal, right? So since you are having hexadecimal number, what you can do, simply you can place the position weights. Simply you can put the position weights. Okay. 16 power 0, 16 power 1. Now multiply each and every digit with the respective position weight and then add. Whichever number is giving 43, that option will be correct. Even you can verify here. 16 into 2, that is 32, plus 11 is nothing but 43. Yes, we are getting. So whenever MCQ question is there, you are getting more than one method. Okay. You can solve the same question in n number of methods, right? So whichever method you feel comfortable, you can proceed like that. Okay. Right. Yes, very good, Giritharan, very good. Yes. So up to now we got among 4 choices. With the help of this one, we are able to eliminate 2 choices. Now 2 choices are having regarding hexadecimal number, same number. Okay. Now the other part of the question is what? Represent the decimal number 43 in BCD. BCD. It is very simple. 43 is the decimal number. We have to represent in BCD. So here 4 is nothing but 0100 and 3 is nothing but 0011. This is the BCD code. Either you can represent each and every decimal digit with 4 bits like this, or otherwise you can just do the grouping of 4 bits. Here 0011 is nothing but 3, 0100 is nothing but 4. Yes, option B is the correct one. So option C you can eliminate. Here in option C you are having 3, you are getting here, 4 you are getting here. But here you are having the decimal number 43. 43. Okay, right. So in this way, whenever you are solving any gate question regarding digital circuit subject, okay, whenever you are having the questions MCQ, okay, either the same question you can solve in the conventional approach, that is the step by step you can solve, and that is the direct method or forward method, and other way is you can do the reverse approach, that means with the help of option elimination or whatever. In this question if you observe, that is regarding number system conversion. Either according to the question you can solve the question in the forward method, so these two are the like forward method. Otherwise you can verify option by option whichever with the help of, by looking at the 4 choices, okay, regarding hexadecimal number, 2 choices are having same number, other 2 choices are having same number, okay. So the moment if B2 is not giving 43, straight away you can eliminate A and D. So with the help of that you are getting 2 choices. After that you can verify, okay, whichever, by doing the grouping of 4 bits, if you are considering this code is BCD and whichever the resultant value is giving 43, that will be correct. Like that you can solve the same question, okay. And in the previous class also we have discussed variety of shortcuts regarding other concepts, right? Okay. So for this question, option B is the correct answer. Now I want to give one conclusion point. Let us proceed further. Say for example, here you are having the decimal number 43. According to the question, we have converted into hexadecimal. Now for the time being, just convert this number into binary. Just convert this number into binary. Actually we solved the question, but I want to give one conclusion point. Okay. So in order to convert hexadecimal to binary, what is the first step? We have to represent each and every hexadecimal digit with how many bits? Each and every hexadecimal digit we have to represent with how many bits? Yes, we have to represent with 4 bits, right? Yeah. So here 2 is nothing but 0010, 0010, and B is nothing but 1011, 1011. Okay. So each and every hexadecimal digit you can represent with 4 bits like this. Yes, very good, Giritharan, very good. After this, this entire number is what? Integer part. So here leftmost side you are having 2 zeros, you can ignore because those are insignificant. Okay. So that means in the resultant final answer regarding the binary number, if you count the number of bits, here total you are having 6 bits. That means for representing the decimal number 43, if you are using unsigned representation, for representing the decimal number 43, actually 6 bits are sufficient. But for representing the same decimal number, if you are using BCD code, we require 8 bits. So when compared to this method, this representation, BCD code is having more number of bits. That is a drawback. But here you are having 8-bit number like this. Now if you do the grouping of 4 bits, directly you can write the corresponding decimal digits. That is the beauty of BCD number system or BCD code. Whereas here, if you do the grouping of 4 bits, you will get the corresponding hexadecimal digits. From here, you have to convert into decimal. That means 2-step procedure is there. That's why whenever after performing any mathematical operation, if you want to display that result in the decimal form on the 7-segment LED or LCD, if this frequency is more, that time better you can use BCD code. Okay, so that is the reason why we are using BCD. Whenever for storing purpose, when you observe these two, here obviously with the help of less number of bits, when you are able to save the same number, obviously you can use that method so that you can store more numbers, right? Yes or no? With the help of less number of bits, if you are able to store a particular number, obviously you can use whatever the memory space is available. In that space you can store more numbers, right? So whenever after performing any result, if your requirement is just to store those results, that time you can use unsigned. But if that result, if you want to display in the decimal form on the 7-segment LED or LCD, then that time better you can use BCD. I hope all of you got the clarity. So with this understanding, let us proceed. The next code is XS3 code. So here just by looking at this word, you are already getting the clue. What is the clue? Here, the name XS, how much? 3. XS3 code. Okay, so that means this code also we are using for decimal digits only. Whatever the BCD code we got, that BCD code you have to add 3, so that whatever the corresponding code you are going to get, that is nothing but XS3 code. So XS3 code is nothing but BCD code plus 3. BCD code plus 3. So here first column same, decimal digits only. If you are having single decimal digit, you will get 10 possible values. Now, here we are writing corresponding XS3. It is very simple. Whatever earlier code we have written, just you have to add 3. Or otherwise, what you can do, whatever the number here you are having, first of all you can add 3 and write the corresponding binary. Both are same. So 0 plus 3 is nothing but 3, 0, 0, 1, 1. Next, 1 plus 3 is 4, 0, 1, 0, 0. So in this way, in the sequence you can write, simple. Okay, just you have to add 3. Earlier we got like 4 zeros to 1 0 0 1. So if you are adding 3, you will get 0 0 1 1 to 1 1 0 0, right? So that means for a single decimal digit, since you are having 10 possible values, the corresponding XS3 code you are getting 10 possible combinations. But here you are getting for 4-bit, yes or no? What are the 10 possible combinations you are getting for 4-bit? But in general, if you are having 4 bits, total how many combinations you are going to get in terms of zeros and ones? If you are having 4 bits, total how many combinations in general we will get? Yes, if you are having 4 bits, total you will get 16 combinations, yes or no? But among the 16 combinations, or out of the 16 combinations, we are using only 10 combinations. The remaining 6 combinations are non-valid XS3. The remaining 6 combinations. What are those? Here at the starting, you will be having 3 combinations. At starting, you will be having 3 combinations, and at last, you will be having 3 combinations. So these are the non-valid XS3. These are the non-valid XS3. Okay, just like in the BCD code, we got first 10 combinations are the valid BCD. After that, remaining 6 combinations are non-valid. Whereas in XS3 code, here the starting 3 combinations and last 3 combinations, those are non-valid XS3. Okay, right. So in the last class, regarding 1's complement, 2's complement we have discussed. Okay, regarding 1's complement, say for example, if you want to perform 1's complement of 0, directly what I have told, complement of 0 is nothing but 1. Similarly, if you are having 1, 1's complement of 1 is nothing but just you have to complement that bit. That's all. I have told like that. But the actual meaning of 1's complement is, so here you are having what? We are considering binary number. We are considering binary number, right? So whatever the single bit you are having, each bit you can subtract from 1. Each bit you can subtract from 1. In the binary number system, each and every bit you can subtract from 1, because in the binary number system the maximum that you can represent is 1. That's why we can easily subtract each and every bit from the maximum value, that is 1. Okay, so here 1 minus 0 is nothing but 1. Here 1 minus 1 is nothing but 0. So this is the meaning of 1's complement. Okay, this is the meaning of 1's complement. So but here if you observe, whatever the resultant value you are getting, 0 is simply becoming 1, 1 is simply becoming 0. That's why this shortcut I already discussed in the last class. Okay, but actual meaning of 1's complement means each and every digit or each and every bit you have to separate from 1. From there you will get 1's complement. After that, if you are adding 1, you will get 2's complement. You will get 2's complement. In the same way, in each and every number system, you will be having two types of complement. The first one is radix complement, that is r's complement, and the other one is r minus 1's complement. Say for example, for easy understanding, let us consider decimal number system. So if you are considering decimal number system, now tell me what are the two types of complement you will get in decimal number system. Giritaran, what is the answer? In the decimal number system, what are the two types of complements we will be having? See, in the decimal number system, base value is what? 10. So just consider r is nothing but 10. So you will get 10's complement, and here substitute 10. 10 minus 1 is nothing but 9. 9's complement. Right? So that means in the decimal number system you are getting two complements. One is 9's complement, other one is 10's complement. Okay. So in the decimal number system, for a single digit, the maximum value that you can represent is 9. That means each and every digit, if you are subtracting from 9, what are the resultant value you are going to get? That is nothing but 9's complement. After that, if you are adding 1, you will get 10's complement. Like that. In each and every number system, you will be having two types of complement. It is very simple. In the each and every number system, for a particular digit, whatever the maximum value that you can represent, if you are subtracting each and every digit from that maximum value, from there you will get r minus 1's complement. After that, if you are simply adding 1, you will get r's complement. That is the reason. In the last class, I have mentioned that 2's complement is nothing but 1's complement plus 1. This is the reason. How you are going to get r's complement? If you are adding 1 to the r minus 1, from there you are going to get r's complement, right? So this is the conventional method or exact meaning of r minus 1's complement, or how we have to find the complement. But whatever the concept in the last class we have discussed regarding 1's complement or 2's complement, those are the shortcut methods. I hope all of you got the clarity regarding the r's complement and r minus 1's complement. Now you might be wondering that why I am discussing this concept now. Okay, just wait for a couple of seconds. You will get the beauty of the accessory code or the significance of accessory code. Just wait for a couple of seconds. So with this understanding, now tell me, say for example, I want to find out 9's complement of 4. I am considering one decimal digit just for easy understanding. Okay, I want to perform 9's complement of 4. So just now I have mentioned the real definition of the r minus 1's complement. So what you have to do? You have to subtract this digit from 9. Yes or no? So 9's complement of 4 is nothing but 9 minus 4. So from there you will get 5. From there you will get 5. 9's complement of 4 is nothing but 9 minus 4. From there you will get 5. Now here if you observe, in order to find the 9's complement in the decimal number system, in order to find the 9's complement in decimal number system, you have to perform what operation? You have to perform subtraction operation. You have to perform subtraction operation. Now, if you want to eliminate this particular subtraction operation, whenever you want to find the 9's complement or 10's complement for the decimal numbers, okay, first of all, you have to find the 9's complement. After that, if you are adding 1, you will get 10's complement. That's all. Okay. Now, in order to find the 9's complement, you require the subtraction. You have to perform the subtraction. Now, if you want to eliminate this subtraction, okay, I want to get the 9's complement of 4. The final answer is what? 5. The final answer is 5. Now, without performing the subtraction operation, now if I am going to get this final answer. Okay, I will just show you how I am going to get this final answer with the help of XS3. See, just carefully observe. Here I have considered the number 4. So for 4, we want to calculate 9's complement, right? So just consider here for 4, we are having the XS3 code is what? 0111. Okay. Now, whatever the XS3 code you got, just apply 1's complement. What is the number you are going to get? Just apply 1's complement to this number. It is very simple. Wherever zeros are there, replace with 1. Wherever 1's are there, replace with 0. So that means you will get this number or not? 0 complement is 1. 1 complement is 0. Yes or no? So that means here for 4, the corresponding XS3 code is what? 0111. Here I am using simply 4 NOT gates. Okay. With the help of NOT gates, we can complement each and every bit. We can complement. Right. Now just observe. Whatever the code here you are getting, regarding that, the corresponding decimal digit is nothing but what? 5. So final answer we are getting. Right. So here conclusion point is what? So you can write the definition regarding self-complementing code. Whenever any code, if it satisfies like this condition, then we will call it as self-complementing code. So just make a note. A binary code is said to be self-complementing code if 9's complement of decimal digit is equal to 1's complement of the code corresponding to it. So here we want to get 9's complement of decimal digit, but that final answer you are going to get whatever the code for that particular decimal digit you are having. For that decimal digit, I have considered the code. I am just applying 1's complement. That's all. 1's complement we can easily get with the help of NOT gates. That means we are eliminating this kind of subtraction operation. Okay, right. So whenever any code satisfies like this condition, then that particular code we can call it as self-complementing code. Okay, right. So you can observe for remaining cases. Say for example, if you want to perform 9's complement of 0, that means 9 minus 0 is nothing but what? 9. 9 minus 0 is 9. So just complement all the bits here. 0 0 1 1, complement means 1 1 0 0, right? Similarly, 9's complement of 1 is 9 minus 1, that is 8. 0 1 0 0, 1's complement you will get 1 0 1 1. Similarly, 9 minus 2 is 7. 0 1 0 1, complement means 1 0 1 0. In this way you will get 9 minus 3 is 6. 9 minus 4 we already discussed. Similarly, vice versa. Okay, right. So here for all the numbers it is possible. Okay, see, if you observe the BCD code, if you observe the BCD code here, if you observe the BCD code here, you are having 4 bits as what? All the bits are zeros. Okay, if you complement all the bits, you will get 4 ones. 4 ones is not at all valid BCD, not at all valid BCD. So this kind of feature is not there in the BCD code. That's why in the earlier days, in the decimal computers, that means you are given the inputs in the form of decimal form. Okay, that time if you want to perform any kind of radix complement or diminished radix complement, or if you want to perform the subtraction operation with the help of complement method, that time directly on the decimal number system, if you want to perform such kind of operations, okay, obviously you require the help of what? Complement technique. Okay, but that kind of feature was not there in the BCD code. So in order to get the resultant final complement output easily, that feature you are able to get in XS3 code. Okay, that is the beauty of XS3 code. That's why whatever the BCD code you are having, we have added 3. The reason is that one. Okay, here each and every decimal digit, okay, you can easily subtract from 9. That is nothing but resultant value is nothing but 9's complement of that particular decimal digit. The resultant value you are going to get just by performing 1's complement of the code corresponded. That's all. That's all. Here you no need to perform any subtraction. If you are doing manually, you have to perform subtraction. But in order to eliminate this subtraction, we are using XS3 code. Earlier days, XS3 code was used in the decimal computers. Decimal computers. Okay, right. Next one, put the side heading sequential code. Sequential code. It is very simple. As the name implies, sequence is there, right? So it is very simple. If the difference between successive codes, if the difference between successive codes is equal to 1, so whatever the code you are placing, okay, if you consider any two successive codes difference, that means you can separate smaller from larger so that you will get magnitude wise 1. Okay, right. So otherwise if you are adding 1 to the previous one, you will get the next code like that. Okay, you are getting the code in a sequence, okay. So if you observe here, regarding BCD code, here you are having, if you are subtracting, you can consider any two successive codes, subtract the smaller code from larger so that you will get difference as 1, because here we are placing the code for the decimal digits. Here these decimal digits you are going to get by adding 1 to the previous one. Otherwise, if you are subtracting the previous from the next one, you will get the value as 1. Okay. Similarly, XS3 code also we have written for decimal digits. That means whatever the BCD code and XS3 we have discussed, those two are the examples of what? Sequential code. Those two are the examples of sequential code. Examples of sequential code are nothing but BCD code and XS3. BCD code and XS3 code, these two are the examples of sequential code. Okay, I hope all of you got the clarity what is the meaning of sequential and how these two codes come under examples of this sequential code. Okay, right. Now, say for example, if you are having a building, it consists of, say for example, 16 floors. Okay, if you want to go to the top floor, whether you will prefer staircase or you will prefer lift. Obviously you will prefer lift only, right? Even if you are having 3 floors or 5 floors, okay, in the building, if lift is available, definitely you will prefer lift only, right? If lift is not there, then only you will prefer staircase. Even for 3rd floor, if lift is there, obviously we will prefer lift only, right? So in the same way, suppose if you are having a building, if it consists of 16 floors, okay, 0, 1, 2 and so on, 15th floor, okay. Say for example, you are going from ground floor to the top floor, okay, that time obviously you will use the lift, okay, right. Suppose currently the lift is in 7th floor, okay, then it will display the value 7 on the 7 segment LED, okay. And suppose if it reach to 8th floor, then it will display 8 on the 7 segment LED. On the 7 segment LED, it will display the value as 8, okay. Now here if you observe, these two are the adjacent floors, 7 and 8 are adjacent, but here if you are using internal code, say for example unsigned case, if you are considering 7 is nothing but 0,111, 7 is nothing but 0,111 and 8 is nothing but 1,000. Okay, if you are considering unsigned case, if you are considering the corresponding code unsigned, here what will happen? Just observe here, all the bits have to complement, even though 7 and 8 are adjacent numbers, but if you are using internal code is unsigned, here all the bits have to be complemented, okay. Suppose if you are having very large number, that means it is having multiple bits, okay, due to any reason, if some of the bits couldn't get complement, okay, due to any reason, or if some bits are getting more time in order to get complement, then whatever the final result you are going to get, is it correct result? No, right? So you are getting wrong result, right? So in order to avoid such kind of issues in the real time, okay, so now we will place the code in such a way that only one bit will be complemented, okay, right. So what is the drawback is there in the sequential code? That drawback we can easily overcome with the help of, if we are able to arrange, okay, any two successive codes, if only one bit is getting deferred, then it is easy, okay, and you will get lot of advantage with the help of that particular code. And that code, the name of that particular code is nothing but unit distance code. Here, as the name implies, unit means one, distance, okay. When you are observing any two successive codes, only one bit will differ, that's all. A binary code is said to be unit distance code if the number of bit positions differed by successive codes is equal to 1, then we will say that particular code is what? Unit distance code. If the number of bit positions differed by successive codes is equal to 1, that's all, okay. So how we are going to get, now let us see, that is the beauty of unit distance code. So can you guess what is the example of unit distance code? I hope all of you can guess. If you are attending this session, I already mentioned earlier the examples of each and every code. Regarding numeric code, example is what? BCD, we already discussed. Regarding non-weighted code or unweighted code, regarding weighted code, BCD code is an example. Regarding unweighted code, we already discussed XS3. And what is the other code? Yes, the other code is gray code. Yes or no? Gray code. So gray code is an example of unit distance code, okay. Gray code is an example of unit distance code. Now let us see how to formulate how to formulate the gray code of n plus 1 bits with the help of gray code of n bits. Say for example, let us start the gray code for 1 bit. Gray code for 1 bit. If you are having 1 bit, obviously you are getting two combinations, 0 or 1. So here if you observe, these two are differed by only 1 bit. Okay, there is no confusion here. Now, with the help of gray code of 1 bit, now let us formulate the gray code for 2 bits. Gray code for 2 bits. It is very simple. Whatever the gray code of 1 bit we got here, just copy as it is. Gray code of 1 bit is nothing but 0 1, 0 1. Just copy as it is. Now, just consider, suppose if there is one mirror here. Suppose if there is one mirror, then you will get mirror image. Okay, you will get 1 here and then 0 here. First step is, whatever the gray code of 1 bit you got, just copy as it is. After that, assume that there is a mirror. If there is mirror, then you will get mirror image. Sorry. Okay. After this, what is our requirement? We want the gray code of what? 2 bits. We want the gray code of 2 bits. Okay. So other bit, what you can do, for first half combinations, here total we are getting 4 combinations, right? So the first half combinations, you can put simply 0. The other half of the combination, simply you can put 1. That's all. Simply you can put 1. Now you can observe here, 0 0 0 1, only 1 bit is changing. 0 1 to 1 1, only 1 bit is changing, this bit. 1 1 to 1 0, only this bit is changing. Okay. And here if you observe, even the last code and first code, if you observe, only 1 bit is changing. Okay. So actually whatever the code here we are arranging, if you consider any two successive codes, only 1 bit is getting deferred. That is the meaning of unit distance code. Even regarding the gray code, we are getting one more special feature. Even the last code and first code, that means after this code, if you are just simply copying the first code, even those two codes also differing by 1 bit only. That means it is forming what? Cyclic code, right? Next one, suppose now you got the gray code of 2 bits. Now with the help of gray code of 2 bits, now let us formulate the gray code of 3 bits. Gray code of 3 bits. What is the first step? Whatever the gray code of 2 bits you are having, just copy as it is. 0 0 0 1 1 1 1 0. This is the gray code of 2 bits. Now you have to consider there is a mirror here. If there is a mirror, then you will get mirror image 1 0 1 1 0 1 0 0. Okay, right. Here if you observe, total you are getting 8 combinations. That means first 4 combinations you can put simply 0. First 4 combinations you can put simply 0. And the remaining 4 combinations you can put simply 1 regarding the first bit. Now here also if you observe any two successive codes you can observe, only 1 bit will differ. Even the last code and first code, if you observe, only 1 bit will differ. Okay, that is a cyclic code. In this way, you can further continue. Similarly, if you want to formulate the gray code of 4 bits, you can consider the gray code of 3 bits as it is. After that, you can consider mirror and you write the mirror image. And then the leftmost bit, 4th bit, you can put for 8 combination 0, other 8 combination 1. In this way, you can continue for any number of bits. Just you can start from 1 bit, then you can extend bit by bit, you can add. Okay, and then you can continue for any number of bits. Okay, whatever the code here you are arranging, this code is nothing but gray code. You can formulate the gray code in this way for any number of bits. Okay, in this cyclic process, step by step, you can extend and you can formulate based on the requirement. And here, while you are creating for the example for unit distance code, and inherently one more logic was there, that is the cyclic code, right? So here you are having the topic side heading. It is a simple topic, cyclic code. Regarding that, we already mentioned. So whatever we have discussed here, 3-bit gray code, 3-bit gray code, this one I have just arranged in the circular form. Simple. You can observe here 000, then 001, 011, 010, 110, 111, 101, 100. You can observe here. Here the last code you got 100, right? Now 100 was there, 000 is there. Only one bit is changing. Even the first code and the last code are getting differed by 1 bit only. That's why we can arrange the gray code in the cyclic manner also. Okay, whatever the successive codes are there, those are getting differed by 1 bit. Even the last code and first code also are getting differed by 1 bit. Okay, so that's why we can use gray code in number of applications. Okay, because here we are getting lot of advantage. You can observe here, while you are moving from one sector to another sector. See, here you are having one circular shape. This circular shape, for the time being, I have made partition into 8 parts. That means you are getting one sector. Like that, you are having 8 sectors, right? So each sector, from each sector you will get some angle, right? So each sector you can represent with the help of one gray code like this. Since I have made into 8 parts, so I have used the 3-bit gray code. Similarly, if you want to make into 16 parts, that time you require 4 bits, like that. Like that, based on the requirement, you can place the gray code. Okay, right. Now all of you put the heading applications of gray code. So can you guess what is the one of the most application of gray code with respect to our syllabus? If you look at the chapters, from there also you will get the clue. Can you guess where we will use the gray code? Yes, very good, very good. See, if you look at the K-maps, Boolean algebra and K-maps, the second chapter is what? Boolean algebra and K-maps. So while you are doing the simplification with the help of K-maps, there we will use the gray code. Okay, so whatever the min terms we are placing there, adjacent min terms will get differed by only 1 bit. Okay, so that you can easily get the simplified function just by doing the grouping of adjacently placed ones. Okay, regarding that concept we will discuss in the second chapter. Okay, for the timing, note down the applications where we are going to use the gray code. Okay, we can use the gray code in the K-maps. For doing simplification easily. Okay, with respect to our syllabus, we are using gray code in the K-maps in order to get the simplified function easily. Okay, with respect to the real time application, you can observe here. Here I already placed the gray code in the circular form. Okay, for the timing I have represented like this, or if you want you can represent in the clockwise. Okay, based on the requirement you can represent anti-clockwise or a clockwise, no issue at all. Okay, but ultimately either you are considering clockwise or anti-clockwise. Okay, whatever the adjacent codes if you are considering are getting differed by 1 bit only. Okay, in the real time, if you see in the industries, okay, you will be having the mechanical devices or machines will be there which will take the rotation operation, right, which are continuously moving in the circular fashion, right? So that time if you are using unsigned code, okay, what will happen? From one sector to another sector, if you are using 3-bit unsigned code, at some places only 1 bit has to complement, at some places 2 bits have to complement, in the worst case 3 bits have to complement. But if you are using gray code, from one sector to another sector only 1 bit is changing. From one sector to another sector only 1 bit is changing. It is easy. Or you can say that there is a uniform delay. Whenever any mechanical device is taking the rotation operation or circular fashion, okay, either clockwise or anti-clockwise, that time if you are using the gray code, you with the help of gray code, okay, you can find the angular displacement or you can find the position of that particular shaft. Okay, so this is the real time application of the gray code. We can use the gray code to measure the to measure the angular displacement or to know the position of the shaft. And not only that, whenever you are getting any ambiguity because of unsigned or normal sequential code, okay, if you are considering binary number, if you are using in the sequential form, if you are using sequential form, because of that sequential, if you are getting any errors or if you are having any ambiguity regarding your results, okay, in all such cases, in order to get the correct results or in order to avoid all such ambiguities, in all such applications you can use the gray code. In all such applications you can use gray code. So in this particular session we have discussed regarding BCD code, XS3 code and gray code. So regarding these three codes we have discussed in detail how to represent these codes and what is the significance of each and every code. Okay, so with this we have completed the first chapter. So those who couldn't attended the earlier sessions, so kindly watch whatever the sessions we have discussed regarding digital circuit subject regarding first chapter, that is number systems and codes. So kindly watch those video lectures in your free time. So far regarding first chapter we have discussed, we started with the introduction of the digital circuit subject, and then we have discussed the number system conversions, and then we have discussed like basic arithmetic operations, and then how to find the base or radix, and then we have discussed the data representation, and then this is the last topic, that is the binary codes. Okay, this is about the first chapter. So in the next class we will start the second chapter. Okay, so regarding digital circuit subject in our IMS GATE Academy YouTube channel. Okay, so in the next week on coming Thursday and Friday, the session timings will be same, 4 to 5:30, 4 p.m. to 5:30 p.m. So on 27th April, I will discuss regarding basic rules and laws of Boolean algebra. Basic rules and laws of Boolean algebra. And then on 28th April, that is on Friday, we will discuss regarding min terms, max terms, and then Boolean functions. Okay. So all of you kindly share this information with all of your friends so that they also can attend these sessions and they also will get benefited from these sessions. Okay, so today evening we are having regarding math session, okay, regarding foundation course, so kindly attend that session. Okay, if you are from any branch, math subject is common for all the branches, so you can attend the math session. So the students who are from EC, electrical, instrumentation and computer science, so regarding digital circuit subject, in the next week we are having 2 sessions. Kindly share this information with all of your friends, okay, and kindly join the session in live so that you can get maximum benefit from these live sessions. Thank you everyone.